Today, let us see what are the specifications of a digital voltmeter and what is a digital multimeter. So we have seen what the digital instruments are. The digital instrument basic circuits involve the use of logic gates, flip-flops. So logic gate is a circuit that produces a desired high or low output voltage when its several input terminals are all at the prescribed high or low input voltage level. The digital instruments are rapidly replacing the analog instruments because of their easy readability, better resolution, and higher accuracy. So digital instruments display the output in the numerical form, that is the digital form. Digital instruments are used to measure the voltage, current, the power, frequency, etc. To enable digital instruments to recognize information inputs which are analog in nature must be converted to digital form. Hence, any digital instrument consists of an analog to digital converter in its input stage. So the basic building blocks of a digital instrument has an analog to digital converter, next the signal processing, next the digital display. So any digital instrument may consist of several components like the resistors, capacitors, the transistors, the linear ICs, the digital ICs, the display devices, the analog to digital converters, and digital to analog converters. So the display block may be analog or digital in nature. If analog readout is required, a stage involving digital to analog conversion can be included before the display. So the instrument which represents the measured value in the form of a digital number is known as the digital instruments. It works on the principle of quantization. So the quantization is the process of converting a continuous input signal into a countable output signal. So the instruments that are used to express the measuring quantity in numeric format is known as digital instruments. So quantization is the basis of working of a digital instrument. It is an act of transforming an analog signal into its digital form. Digital instruments are composed of the logic circuits that carry out measurement of the quantities. Due to several advantages of digital instruments, such as the high speed, the errorless results, better resolution, and greater accuracy over analog instruments, the popularity of digital instruments are increasing rapidly. Also, the digital instruments display the measured quantity in discrete numerals, thereby eliminating the parallax error and reducing the human errors associated with analog pointer instruments. In general, the digital instruments have the superior accuracy to analog pointer instruments, Many incorporate automatic polarity and range indication, which reduces operator training, the measurement error, and the possible instrument damage through overload. In addition to these features, many digital instruments have an output facility enabling permanent records of measurements to be made automatically. So the advantages of the digital instruments over analog instruments are: digital instruments are superior to analog instruments because of high accuracy, smaller in size, low power consumption, high frequency range, detection of low level signals, the high durability, the good visual readout, and good quality, no human reading errors, and no parallax errors. They have high input range with automatic range selection and overload indication. The input impedance is high, the resolution is better, the output in digital form can be directly recorded, and it is suitable for further processing also with the development of IC chips. The cost, the size, and the power requirement of digital instruments is drastically reduced. So we have seen what a voltmeter is. So a digital voltmeters are essentially analog to digital converters with digital displays to indicate the measured voltage. So digital multimeters are electronic voltmeters with digital displays. So digital voltmeters are measuring instruments that convert analog voltage signals into digital or numeric readout. This digital readout can be displayed on the front panel and also used as an digital output signal. Any digital voltmeter is capable of measuring analog DC voltages. However, with appropriate signal conditioners preceding the input of the digital voltmeter, quantities such as the AC voltages, ohms, that is resistance, the DC and AC currents, the temperature and pressure can be measured. The common element in all these signal conditioners is the DC voltage, which is proportional to the level of the unknown quantity being measured. This DC output is then measured by the digital voltmeter. Digital voltmeters have various features such as the speed, the automation operation, and programmability. The DVM displays AC and DC voltages as discrete numbers rather than as a pointer on a continuous scale as in an analog voltmeter. A numerical readout is advantageous because it reduces human error, it eliminates parallax error, it increases the reading speed, and often provides output in digital form suitable for further processing and recording. With the development of IC modules, the size, the power requirements, and cost of digital voltmeters have been reduced so that the digital voltmeters compete with analog voltmeters in portability and size. The digital voltmeters are classified as the ramp type digital voltmeter, the successive approximation type voltmeter, the dual slope integrating type voltmeters, etc. So we have already seen a ramp type digital voltmeter. The operating principle of ramp type digital voltmeter is based on the measurement of the time that a linear ramp voltage takes to change from 0 volts to the level of the input voltage, or to decrease the level of the input voltage to 0. This time period is measured with an electronic time interval counter, and the count is displayed as the number of digits on an tube or a display. Basically, the ramp type DVM consists of a linear ramp which is positive going or negative going. The range of the ramp may be plus or minus 12 volts, while the base range is plus or minus 10 volts. In this case, a negative ramp has been selected. The operating principle and block diagram of ramp type DVM is nothing but the start of the measurement. A ramp voltage is initiated, the counter is reset to 0, and the sample rate multivibrator gives a pulse which initiates the ramp generator. The ramp voltage is continuously compared with the voltage that is being measured. At the instant and the two voltages becomes equal, a coincident circuit generates a pulse which opens a gate. That is, the input comparator generates a start pulse. The ramp continues until the second comparator circuit senses that the ramp has reached 0 value. The ground comparator compares the ramp with the ground. When the ramp voltage equals 0 or reaches ground potential, the ground comparator generates stop pulse. The output pulse from this comparator closes the gate. The time duration of the gate opening is proportional to the input voltage value. So, in the time interval between the start and stop pulses, the gate opens and the oscillator circuit drives the counter. The magnitude of the count indicates the magnitude of the input voltage, which is displayed by the readout. Therefore, the voltage is converted into time and the time count represents the magnitude of the voltage. The sample rate multivibrator determines the rate of cycle of measurement. A typical value is 5 measuring cycles per second with an accuracy of plus or minus 0.005% of the reading. The sample rate circuit provides an initiating pulse for the ramp generator to start its next ramp voltage. At the same time, reset pulse is generated, which resets the counter to the zero state. The advantage of the ramp type DVM is it is easy to design, its cost is low, a single ramp requires excellent characteristics regarding linearity of the ramp and time measurement. But there are disadvantages with this ramp type DVM. There are large errors are possible when noise is superimposed on the input signal. So input filters are required for reduction of the noise. The next type digital voltmeter, the successive approximation type digital voltmeter, it performs analog to digital conversion known as digitization. So in the block diagram of a successive approximation type digital voltmeter, when the start pulse signal activates the control circuit, the successive approximation register is cleared. The output of the SAR is 00000000. The output voltage of the D to A converter is 0 volts. At the beginning of each measurement, a start pulse is applied to the start-stop multivibrator. This sets 1 in the MSB of the control register and zeros in all bits of the least significant, that is other bits. So when the control register is 8-bit register, its reading would be 1 followed by 7 zeros. This initial setting of the register causes the output of the D2A converter to be half of the reference voltage, that is half V. This converter output is compared to the unknown input by the comparator. If the input voltage is greater than the converter reference voltage, the comparator output produces an output that causes the control register to retain 1 in its MSB, and the converter continues to supply its reference voltage as half V. The ring counter then advances by 1 count, shifting a 1 in the second MSB of the control register, and its reading becomes 11000000. This causes the D2A converter to increase its reference output by 1 increment to 1/4 volts, that is half volts plus 1/4 volts. And again it is compared with the unknown